Have you ever looked up and seen a glider just hanging in the air, seemingly effortlessly? It makes you wonder, like, how do they actually stay up there?
Yeah, it's not magic or anything,
No, definitely not magic.
but it is really cool.
It is. It's this amazing dance between the pilot and the forces of the atmosphere, right?
Exactly. It's all about understanding how the air moves, where the lift is, and how to use it to your advantage.
And for glider pilots, I mean, understanding the weather isn't just like a nice-to-have skill.
Oh, no.
It's absolutely essential. I mean, unlike powered aircraft, they can't just rely on an engine to keep them aloft.
Right. They're totally at the mercy of Mother Nature, you could say.
Yeah, they have to find those rising currents of air at the lift that are moving upwards faster than the glider is sinking.
And that's what we're going to be diving into today.
Yeah, that's our mission today.
Really unlocking the secrets of glider weather.
It's like the whole world up there.
It is, and it's fascinating, actually.
So for this deep dive, we're going to be exploring the essential weather knowledge that every glider pilot needs, really getting into the nitty-gritty of it.
Right. And we've been looking at this amazing document called GFH9.pdf, I think.
Yeah, it's a bit of a mouthful.
It is, but it is absolutely packed with the weather principles that are vital for successful soaring.
It's a great resource.
It is. So today, our goal is to try to pull out some of the key insights from that document, those aha moments that give you that real understanding of what's happening up there.
Yeah, without overwhelming anyone with too much technical jargon.
Right, exactly.
We want to make it accessible.
We do, because it is fascinating stuff.
It is. So think of it as a fast track to understanding glider weather.
That's a great way to put it.
So ready to soar into this with us?
Let's do it.
All right, so let's start right at the beginning, shall we?
Sounds good.
With the basic building blocks of the atmosphere itself.
Okay, so let's begin with the atmosphere. It's easy to take it for granted. I mean, it's just there, right?
Right.
But without it, there'd be no wind, no clouds, no rain, and definitely no glider flight.
It'd be a pretty boring world.
It would be. And what's fascinating is just how thin this blanket of air really is compared to the size of the Earth.
Yeah, it's mind-boggling when you think about it that way.
It is. Almost all of the atmospheric mass, like 99.9% of it, is within the first roughly 27 nautical miles up.
Wow. So, it seems vast when you look up, right?
It does.
But in reality, it's this relatively shallow layer.
Really puts things into perspective.
It does. Now, when we talk about what the skin is made of, the majority is nitrogen and oxygen.
Those are the big players.
They are. They make up, about 99% of the atmosphere's volume?
Yep, pretty much.
But it's that remaining 1%, those trace gases, especially the water vapor.
Ah, yes.
That's where things get interesting.
That's the stuff that drives all the weather.
Yeah.
That's what makes the magic happen.
Exactly.
So while the proportions of nitrogen and oxygen stay fairly constant even at high altitudes, the amount of water vapor, that can change dramatically depending on where you are and how high up you go.
Right.
So over the tropical regions and over oceans, water vapor can make up as much as 4% of the air, which is actually displacing some of those other gases.
Wow, that's a significant chunk.
It is. But then over deserts or at very high altitudes, it can be less than 1%.
Okay.
So it's a small part, but it is absolutely crucial for forming clouds, precipitation, fog, ice, all the things that directly impact flying conditions.
So we have this atmospheric mix, this air around us, and to understand what's going on up there, we need ways to measure it.
Right? We need to get a handle on it.
And our source, it talks about these three key measurements: temperature, density, and pressure.
Okay, so temperature, I mean, we intuitively understand it, right?
Yeah.
It's about how hot or cold the air is.
Yeah, can I wear shorts or do I need a jacket kind of thing?
Exactly. But scientifically speaking, it's about the energy of those air molecules.
Right, how much they're zipping around.
Yeah, how much they're jiggling and bouncing off each other. The more energetic they are, the higher the temperature.
Okay, that makes sense. So density then?
Density is simply how much air mass is squeezed into a certain space.
So like how tightly packed those air molecules are.
Yeah, exactly. So think of it this way. If you have a balloon full of air and you squeeze it, you're increasing the density of the air inside because you're forcing the same amount of air into a smaller volume.
Okay, that makes sense. And finally, we have air pressure.
Air pressure is the force that all those moving air molecules exert on everything around them. They're constantly bumping into things, creating pressure.
So it's like a constant bombardment of tiny little particles.
Yeah, and we measure it in units like pounds per square inch, inches of mercury, or millibars.
So those numbers we see on weather reports are telling us how much force the air is exerting.
Precisely.
Okay, got it. Now, what's fascinating is the relationship between these three, right? Temperature, pressure, and density.
Right, they're all interconnected. They all influence each other. And that's where the ideal glass law comes in.
Ah, yes, the laws of physics.
Exactly. It describes this relationship, essentially saying that if one of these changes, at least one of the others has to change in a predictable way.
It's all about balance.
Yeah, it's like a seesaw. If you push down on one side, the other side goes up. So if you heat air, for instance, it becomes less dense and wants to rise. This fundamental law governs how air behaves in the atmosphere, which directly affects glider flight.
Right, because changes in air temperature will directly impact air density and thus the aircraft's performance.
Exactly. And this is especially important on hot days when the air is less dense, which means less lift for the glider.
Makes sense. Now, to try to make sense of all these measurements and have a common reference point, scientists developed the International Standard Atmosphere, or ISA, right?
Yeah, ISA, think of it as a baseline set of typical atmospheric conditions at different altitudes.
A standard, if you will.
Exactly. It's like a common language that everyone in aviation can use.
It's essential for calibrating instruments and for looking at how an aircraft should perform under ideal conditions.
Yeah, and at sea level, under ISA conditions, the pressure is 29.92 inches of mercury,
Okay.
and the temperature is 15 degrees Celsius or 59 degrees Fahrenheit.
So that's what we consider standard at sea level.
Right. Now, starting from that sea level ISA, we have what are called standard lapse rates, which describe how temperature and pressure typically change as you go up in altitude.
So it gives us an idea of what to expect as we climb.
Yeah, below about 36,000 feet, the standard temperature decreases by about 3.5 degrees Fahrenheit or 2 degrees Celsius for every 1,000 feet you climb.
Okay.
And for pressure below 10,000 feet, it drops by about 1 inch of mercury for every 1,000 feet.
All right, so these lapse rates help us predict how the temperature and pressure will change as we go up.
Exactly.
But, and this is a big but,
A very big but.
it's crucial to remember that ISA is just a standard.
Right, a theoretical model.
It's like a perfect textbook example. But the real atmosphere, it's constantly changing.
It's always in flux.
So the actual conditions will often be different from those standard values.
Absolutely.
Right, and as we ascend through this atmosphere, we encounter different layers, right?
Right, it's not uniform all the way up. It's like a layer cake.
It is, each layer defined by how the temperature changes with height.
Exactly.
So we have the troposphere, which is closest to the ground.
That's where we live.
Yeah, that's our home.
It is.
Then above that, we have the stratosphere, mesosphere, thermosphere, and way out at the edge, the exosphere.
Right, but for glider pilots, the troposphere is where it's at.
That's their playground.
That's where all the action happens.
Yeah,
It's the layer where almost all the weather we experience occurs.
yeah.
It extends from the surface up to an average of about 36,000 feet, although that height varies.
Yeah, it's higher near the equator.
Right, and lower at the poles.
And even changes with the seasons.
Yeah, the atmosphere is constantly breathing and shifting.
It is.
But within the troposphere, you'll find thermals, mountain waves, sea breeze fronts, all the sources of lift we'll be discussing.
So that's where the fun stuff happens.
That's where the magic is.
Now, at the very top of the troposphere, we have the tropopause.
Right. Think of it as the boundary between the troposphere and the stratosphere.
Okay.
The air pressure up there is only about 10% of what it is at sea level.
Wow, that's thin air.
It is. And the temperature reaches its lowest point around negative 55 degrees Celsius.
Brrr.
Yeah, pretty chilly. And that tropopause, it's associated with some important weather features like the tops of thunderstorms, clear air turbulence, and those high-speed winds called jet streams.
Right. So it's a significant area, even though we don't typically fly in it.
Absolutely. Now, above the tropopause, we have the stratosphere.
Right.
The air here generally moves more horizontally than vertically.
Okay.
Initially, the temperature doesn't change much with altitude, but then it starts to increase, reaching a peak at around 160,000 feet. Yeah, interesting, isn't it? Now, glider pilots can actually reach the lower parts of the stratosphere by using mountain waves, which we'll get to later.
Okay.
But at those high altitudes, you definitely need supplemental oxygen.
For sure.
The layers above the stratosphere, they're scientifically interesting, but they're not really relevant for glider operations.
All right, so we've got this layered atmosphere. Now, within it, weather events unfold on vastly different scales, right?
Yeah, they do.
Our source breaks it down into microscale, mesoscale, and macroscale.
Right, like a zoom lens.
Yeah, that's a good analogy.
So microscale is the smallest. Think of something like an individual thermal, maybe a few thousand feet across, lasting from seconds to minutes.
Okay.
Macroscale is the big picture. Things like global wind patterns, jet streams stretching across thousands of miles, lasting for weeks or even months.
So from tiny thermals to giant weather systems.
Exactly. Now, for soaring pilots, the most important scale is mesoscale.
That's the sweet spot.
Yeah, it covers weather phenomena that span from 1 to 1,000 nautical miles and have lifespans from minutes to weeks.
Okay.
This includes things like mountain waves, sea breeze fronts, even thunderstorms.
Gotcha.
And it's important to realize that these scales aren't separate. Smaller features, like our microscale thermal, can be embedded within a larger mesoscale system, such as a sea breeze front, which itself is influenced by macroscale weather patterns. It's like a set of Russian nesting dolls of weather.
I like that analogy, weather nesting dolls.
Yeah. And our source points out that predicting gliding weather is particularly tricky because so much of what we're interested in falls into those smaller mesoscale and microscale categories.
So it's inherently more difficult to forecast precisely.
Right, compared to those large-scale systems.
This means that glider pilots, they really need to develop their own understanding of how lift forms and behaves, right?
Absolutely, they need to become weather detectives in a way.
Yeah, to read the skies.
Exactly. And speaking of lift, that brings us to the exciting part. How do gliders actually climb?
Yeah, let's get into the nuts and bolts of how they stay aloft.
Okay, so the most common type of lift is called thermals.
Thermals,
They're the foundation of glider flight.
like the bread and butter for glider pilots?
Exactly. In simple terms, thermals are rising currents of air caused by the sun heating the Earth's surface unevenly.
Okay, so the sun warms up the ground, and that heat then transfers to the air just above it,
Exactly.
making it less dense and causing it to rise.
Right. But what's fascinating is that it's not just about a sunny day.
Right.
Our material emphasizes that subtle differences in atmospheric conditions can be the deciding factor in whether a seemingly perfect day will produce good usable thermals or not.
So there's more to it than what's the eye.
There is. Understanding these nuances is a vital skill for glider pilots.
It's like they need a sixth sense for thermals.
Yeah, almost. Now, how do thermals actually work? Our source describes two main models, the bubble model and the column or plume model. So the bubble model envisions a thermal rising, like a self-contained ring of air, with the air in the center going up and air around the edges thinking back down. This could explain why sometimes two gliders in the same thermal might experience different rates of climb.
I see. So it's not necessarily a uniform upward motion throughout the entire thermal.
Right, it can be quite dynamic.
Okay. And then the column or plume model.
The column or plume model, where warm air flows continuously upward, like a chimney or a stream, this seems to align more with what pilots often experience. You might have a glider lower down latching onto the same rising air that another glider higher up is circling in. It's likely that real thermals exhibit characteristics of both, maybe with bubbles forming within a larger continuous column.
So a hybrid of sorts.
Yeah, it probably depends on how the warm air is being generated at the surface.
Okay, that makes sense. Now, regardless of the exact shape, our source notes that the strongest lift is usually found in the core of the thermal,
Right, in the center.
weakening as you move toward the edges.
Exactly. It's like a bull's eye. You want to aim for the center,
Right in the middle.
but in reality, thermals are often asymmetrical. They can be lopsided.
So it's not always a perfect circle.
No, it's rarely a perfect circle. And they tend to expand as they rise.
Okay.
So they might be narrower closer to the ground and wider at higher altitudes.
Like an inverted tone.
Exactly. And if there's wind, or what we call wind shear, a change in wind speed or direction with height,
Right.
these thermal plumes can tilt over or even break apart, becoming quite turbulent.
So things can get pretty bumpy in a thermo.
Oh yeah, definitely.
Okay. Now, the big question is, when will thermals actually develop?
Right. And how strong will they be?
This is where the concept of atmospheric stability comes in, right?
Right. Stability is key.
So help us understand this. What does it mean for the atmosphere to be stable or unstable?
Okay, so a stable atmosphere, it resists vertical movement.
Okay.
So if you push a parcel of air up or down, it'll tend to return to its original altitude.
Like a rubber band snapping back?
Exactly. Conversely, an unstable atmosphere that encourages vertical motion.
Okay.
So a displaced parcel of air will keep moving in the direction it was pushed. And a certain degree of instability is necessary for thermals to form.
So we need that instability for lift.
We do, but too much moisture and instability, that can lead to thunderstorms.
Which glider pilots they definitely want to avoid.
Yeah, thunderstorms are not a glider's friend.
No. Okay, so how do we get a handle on this stability? Our source introduces the concept of the dry adiabatic lapse rate, or DALR.
The DALR, that's a mouthful.
It is.
But it's an important concept.
It is. So break it down for us.
Okay, so the DALR is the rate at which a parcel of dry, unsaturated air cools as it rises. It's about 5.4 degrees Fahrenheit or 3 degrees Celsius for every 1,000 feet.
Okay.
By comparing the temperature of this rising parcel to the temperature of the surrounding air at different altitudes, we can get an idea of whether the atmosphere is stable or unstable.
Okay.
If the rising air is warmer than its surroundings, it will continue to rise. That's unstable.
That's what we want.
That's what we want for thermals, but if it's cooler, it'll sink back down. That's stable.
No thermals then.
Not so much. And our material has this great visual example of this in figure 9 to 10. It's worth checking out.
All right, so that figure illustrates that things aren't always fixed, right?
No, they're not.
A layer of stable air can become unstable if the ground heats up significantly during the day or if the air higher up cools down.
Exactly.
So conditions can change throughout the day.
Absolutely.
Conversely, cooling at the surface, like on a clear night, or warming aloft can increase stability and suppress thermal activity.
Right, so even if the day starts out unstable, it can stabilize later on.
Okay. And then we have temperature inversions.
Inversions. They could be a real bummer for glider pilots.
Yeah, because they put a lid on thermal development, right?
Yeah, that's where the temperature actually increases with altitude instead of decreasing.
Okay. So the air gets warmer as you go up.
Yeah, which is the opposite of what normally happens.
Right.
And this creates a very stable layer, trapping the warmer air below and preventing it from rising further.
So no thermals can punch through that inversion layer.
Nope, they're effectively capped.
Gotcha. Okay, so what happens if the air isn't dry, like if it's humid?
Right, that's where the saturated adiabatic lax rate, or SALR, comes in.
Another mouthful.
It is. But it basically describes how moist air cools as it rises. And as that moist air rises and cools, it eventually reaches a point where the water vapor starts to condense, forming clouds.
Right.
And this condensation releases heat.
Interesting.
It does. And this release of heat, it partially counteracts the cooling effect of the rising air. So saturated air, it cools at a slower rate than dry air.
Okay.
And the SALR, it's not a fixed number. It varies with altitude, but it's always less than the DLR.
Gotcha. All right. So all this talk about lapse rates and stability, it helps us understand what kinds of air masses are most favorable for good thermal soaring.
Right. So generally, you're looking for cooler air aloft and relatively dry conditions near the surface.
Okay.
This allows the sun to heat the ground effectively
Right.
and limits the formation of too many cumulus clouds that could block the sun.
We want those puffy clouds, but not too many of them.
Right.
Okay.
High-pressure systems often bring these conditions, sometimes with an inversion layer that acts as a cap, preventing clouds from growing too tall.
Right, like we talked about.
Exactly.
However, those inversions, they can also lower and eventually shut down thermals after a few days.
Yeah, they can be a middle-edged sword.
Right. Now, our source also points out some interesting regional variations. For example, in the desert Southwest, during the summer, intense heating of that dry ground can create fantastic thermals that reach very high altitudes.
Yeah, that desert heat is amazing.
It is. And then we have those amazing formations called cloud streets.
Cloud streets. They're like highways in the sky.
They are. They form when those puffy cumulus clouds organize themselves into these long lines, often running parallel to the wind.
Right, and these streets, the mark areas where the air is rising under the clouds and sinking between them.
Okay.
And a skilled pilot can fly straight for long distances along these cloud streets, achieving much better glide performance by staying in the lift beneath the clouds.
So it's all about finding those streets and riding them.
Exactly. Now, what are the key ingredients for these cloud streets to form? Our source mentions an outflow of cold air over land,
Okay.
brisk winds near the surface that are blowing in a consistent direction all the way up to the cloud base,
Okay.
and a wind speed that increases with altitude, with an inversion layer acting as a cap.
So a specific set of conditions.
Yeah, it's like a recipe for cloud streets.
And the distance between the cloud streets, it's typically about 3 times the height of the clouds?
Yeah, that's a good rule of thumb.
Okay. Interestingly, there can also be thermal streets.
Right, similar patterns of rising and sinking air, but without the visible clouds.
So they're invisible highways.
They are, but they're much harder to locate and use.
It's like flying blind.
Yeah, almost. Now, even above those cloud streets, if the wind aloft are just right, blowing across the direction of the streets, you can sometimes get what are called thermal waves forming.
Thermal waves, that's a new one.
Yeah, so they form in the stable air above that inversion layer. And these waves, they can provide additional lift for gliders.
So it's like bonus lift.
Yeah, it's like catching a second wave.
Okay. And speaking of waves in the atmosphere, let's talk about slope soaring.
Okay, slope soaring, that's a completely different principle than thermals.
Yeah, no rising warm air here.
Right, instead of rising air heated from below, slope soaring relies on the wind being forced upwards as it blows against the windward side of hills, ridges, or mountains.
It's like the wind hitting a wall and being deflected upwards.
Yeah, think of it as a ramp.
Okay, so the terrain itself is creating the lift.
Exactly.
But our material points out that not all terrain is created equal, right?
No, it's not. Isolated hills, they tend to disrupt the airflow, causing it to go around rather than up. What you really need is a substantial feature, ideally a ridge that stretches for at least a few miles, to generate that consistent lift.
So the longer the ridge, the better.
Generally, yes.
Okay.
Even a relatively low ridge, say 100 to 200 feet high, can provide lift, although you might not be able to climb much above it.
Right, so we're looking for long ridges. ideally.
Yeah, for the best slope soaring conditions. Now, the musical lift, it typically extends upwards to about 2 to 3 times the height of the ridge.
Okay.
And the strongest lift is generally found when the wind is blowing at a speed of around 10 to 15 knots.
Okay.
And it's coming in at nearly a right angle to the ridgeline, although you can still get some lift even if the wind is angled up to 30 or 40 degrees off.
So it's not super picky about the wind direction.
Not too picky, no. But it is important to be aware of potential changes in wind speed with height, especially over those higher ridges.
Right, because the wind can be stronger or weaker at different altitudes.
Exactly. And that can affect the lift. Now, where you find the best lift, that also depends on your altitude relative to the ridge.
Okay, so it changes as you climb.
It does. If you're below the crest, the best lift is usually close to the ridge itself. But as you climb above the crest, the area of maximum lift shifts further upwind.
Interesting.
Yeah, isn't it?
So you have to adjust your position as you climb.
You do. Now, our source cautions about areas of swirling air and turbulence that can form on steep upwind slopes.
Okay, so those areas can get a bit dicey.
They can. And an ideal slope for a ridge is around a 1:4 ratio. Shallower slopes don't create enough upward push. And very steep slopes, they can generate too much turbulence.
Okay, so it's all about finding that sweet spot, that ideal slope angle.
It is. Now, the stability of the air also plays a significant role in how the slope lift behaves.
Okay, so stability comes back into play here.
It does.
Okay.
In stable air, the lift tends to be smooth and consistent.
Okay, that sounds pleasant.
It is. But in unstable air, you might have thermals rising up the slope, which can be great for gaining altitude, but can also create areas of sinking air on their sides.
So it can get a bit more turbulent.
It can, yeah. And it's crucial to be aware of factors that can weaken or disrupt slope lift, such as terrain upwind that might be blocking the airflow,
Okay.
waves generated by features further upwind, or even sinking air from nearby thermals. The lift can vanish quite suddenly.
That's good to know. So you always need to be aware of your surroundings and the bigger weather picture.
Absolutely. Now, the downwind or lee side of a ridge, that's a completely different story.
Yeah, because as the wind flows up in the top, it's forced downwards, right?
It is, creating those downdrafts.
And ridges with flat tops, they can be particularly tricky.
They can, yeah. They're often associated with sinking air and turbulence. And uneven terrain on the upwind side can also generate those swirling eddies.
So the lee side is generally not a good place to be.
No, not unless you enjoy a bumpy ride.
If you're planning to cross over a ridge in windy conditions, our source advises being prepared for significant sinking air on the lee side.
Right, it's best to plan for it.
And then, of course, we have the three-dimensional effects of ridges with curves or bowl-shaped sections.
Yeah, they can create areas of enhanced lift and also potential sink, depending on the wind direction.
So even more complexity to consider.
It never gets boring.
It doesn't. And finally, if the air being lifted by the slope contains enough moisture, it can cool and condense to form a cap cloud right on top of the ridge.
Cap clouds, they could be beautiful, but also potentially dangerous.
Yeah, because they can lower and even completely obscure the ridge.
Right, and if you accidentally fly into one, you can quickly lose visual references, which can be very disorienting.
Definitely something to avoid.
It is. So it's something to be mindful of when slope soaring, especially in humid conditions.
All right, so we've covered thermals rising from heated ground
Right.
and air being forced upwards by slopes.
Yep.
Now let's delve into something truly powerful.
Okay.
Mountain waves.
Mountain waves, those are the big ranks of soaring.
They are.
They can propel gliders to incredible altitudes.
Yeah, I mean, we're talking record-breaking heights.
Yeah, we are. Records in the U.S. are over 49,000 feet.
Wow.
And in some parts of the world, gliders have even reached into the stratosphere using these waves.
That's incredible. So how do they work?
Okay, so mountain waves form downwind of mountain ranges or even individual ridges when stable air is forced to rise by the terrain,
Okay.
and then it oscillates up and down.
So like ripples in a strom.
Yeah, that's a good analogy.
Okay.
And these waves can generate incredibly strong lift.
Right. It seems counterintuitive though, right?
It does.
Because you'd expect the air on the lee side of the mountain to be sinking,
You would.
not rising.
But these waves can actually tilt upwards with increasing altitude.
Okay.
So you might find yourself experiencing strong lift almost directly above the mountain that created the wave.
Wow, that's amazing.
It is. Now, isolated small hills, they don't typically generate these classic lee waves.
Okay.
But larger, more continuous mountain ranges with a significant difference in height, those are ideal.
So the bigger the mountain, the better.
Generally, yes.
Okay.
Even relatively low ridges can produce usable waves if the atmospheric conditions are just right.
Okay, so it's not just about the size of the mountain, but also the atmospheric.